Chapter 5, Section 6, Factoring a General Strategy. So we've covered a lot of different methods to factor, which goes back even further. We learned shortcuts about how to multiply, and probably the most value about using those shortcuts when we're multiplying, other than saving some time and hopefully less steps. And as long as you do the pattern right, you're going to make less errors. So a very big value of these memorized patterns is to use this in factoring, because factoring is probably the more difficult part of working with polynomials. So they're going to give us some strategies. When we put all this stuff together, all these different methods, we want to take it on in a specific order that they're going to describe here, which is always look for a common factor first. I think I've said that several times in other videos, and the book brings it up over and over and over again. You want to make sure you look for the easiest kind of factoring first, which is that common factor. Then after we've done that, we look at the number of terms. So if we have two terms, like in this case, I have something like a squared minus b squared, one of the things that can happen is this case, which is called difference of squares. Well, to factor that, when I see that pattern, is a very easy pattern to use, and it's a good strategy, and it's an easier one compared to sum and differences of cubes. And we'll go through an example. I think I did an example, I think last section I focused in on an example where you could have used the sum of cubes, or difference of cubes is what it was, and it was like a to the sixth minus b to the sixth. Well, I can also treat that as a difference of squares, which would be just using your power of powers a little bit differently. So look for difference of squares first, and if that's not there, then there's a possibility of a sum of cubes or a difference of cubes. And then we use this pattern to factor. If there are three terms, the first thing to do is look for trinomial that's a perfect square trinomial, they call it, which is a situation where we have a pattern of the first term squared and the last term is something squared. And if I took the square roots of both of those, multiplied them together, and doubled them, then I would determine that, hey, this fits the pattern, and I can factor it into a binomial, the quantity squared. Same thing here, just with a negative. Now, if we end up with 4 terms in the last part of this, if there's 4 terms, the only strategy we've covered is to factor by grouping. So we use that method in doing that too. And the other thing too, I guess, they say it here too, excuse me, with trinomials you can go use FOIL or grouping. Boy, I would focus in on the grouping, even on trinomials. If you get good at that, it's going to save you a lot of time. You're going to have a lot less testing to do to figure out if you've have the right terms in your binomials when you factor a trinomial. So there's a lot of advantages to getting good at grouping. And if you're not sure about that, go back and redo some of those or look at that lesson again. Well, really what they're going to do here, which is nice about the examples in the book, they try to hit most of the major types of situations you're going to run into. Not all of it, but they're going to say, here, what would I apply for a strategy with this type? And we're going to go through that A, B, C, D thing, and the last thing I forgot to mention too was you always check this stuff, okay? And so as we're going through this, let's look at the strategies. I'll talk through the strategies. They talk through it here. You notice here's that A, B. That's referring back to this box of A, B, C, D, right? So their first one here on this factor, x squared minus 20x plus 100, is the A is look for common factors first. And in this case, there's nothing here. The factors of x squared are x and x, and factors of negative 20 X are the prime factors is what I usually look for if you want to find common. If you prime factor things, it's always a pretty good strategy not to miss something that you might miss. Well, this is 2 times 2 times 5 in X. Well, they got an X that's common, but there's no X common in this 100. Okay, so no common factors. Then I have 3 terms. So I'm going to go to, in that B portion here again, they skip here. They say, well, I didn't have 2 terms, so I'm not looking for difference of squares. I'm not looking for sums of cubes or difference of cubes. I have 3 terms. So I stop, I go right to this first, and the best strategy is to look for perfect square trinomials first, and that's what they start looking for. So the way to check for that again is the first term something squared? And yes, it is. It's x squared. And it was 100 something squared, or perfect square. And it is 10 times 10, or 10 squared. So those would be the things that I look at. I have x and 10. If I multiply those together and then double them, do I get 20x? Yes, you do. In fact, you get a negative 20x, or I need to. So the factors of, or the square root of this um, 100 would be negative 10, because negative 10 squared is 102, right? So we use negative 10 for the term of the binomial. So we have x minus 10, and the binomial is squared. Then the other part of the strategy is we make sure that we factor completely. So if I look at my factored thing here, I got x minus 10 and x minus 10. Can I factor x minus 10 any further? And the answer is no in this case. And then the last part is D, is always check. It's easier to multiply than to factor. It's kind of like a comparison between multiplication and division. A pretty good comparison, really, is that, you know, division is usually a little more difficult to deal with, so we always kind of relate it to the multiplication part, saying, you know, like when you're dividing, you know, 10 by 2, that's the same as, you know, they, you know, all the way through grade school, they'd compare it and say 2 times 5 is 10, so we know it must be 5, right? Okay, example 2 is factor 2x cubed plus 10x squared plus x plus 5. Again, I'm going to go through all of these first, right? I'm going to go first, always look for common factors. And in this case, there's nothing again. B then is, well, I have a B portion. It says, well, if you have a binomial, look for difference of squares, sum of cubes, or difference of cubes. Well, I don't have 2 terms. If you have 3 terms, first thing is to look for a perfect squared trinomial. And if that's not there, then use anti-FOIL, like I call it, or FOIL method they call it, or grouping. I would suggest grouping. And here's kind of why, because when you get 4 terms like this one, so in this case it doesn't have 3 terms, so it's a 4 terms in this case, so I have to factor by grouping. Well, grouping is a very nice style. It really brings up a lot of our properties or laws that we've been working with, that allows us to group things if it's all addition. All these terms are added, so I can group them. That's the associative law. That allows me to say, well, let's treat these as a separate group and this as a separate group by putting parentheses around them. And then what I do then is look for a common factor in these groups. And in this case, in this first group, 2x cubed plus 10x squared, the common factor is 2x squared. And then the resultant other factor would be, you know, it's factored out, and then I can get x plus 5. Now, notice that x plus 5 and x plus 5 are, hey, we got a match on something in our terms again. Probably the trickier part about this, I can always factor out 1, can I? I need a coefficient or a number times this grouping, because I need a multiplication plus a multiplication, because I want to then factor these things out here, where this grouping is a common factor, so they factor out x plus 5. and the resulting would be x plus 5 is times 2x squared plus 1. There's my factorization. Okay, next step is, can anything be factored further? So I look at each one of these factors and say, well, x plus 5, no commons. In fact, if I did catch the commons at first, I should not have any common factors factor any out of any of these groups. Those kinds of things. Though if you miss it, that you might be able to catch it at this stage, so it isn't bad to look for that. And then 2x squared plus 1. You know, it's tempting to think, man, maybe this is something squared, but that 2 is not something squared. And we don't have sum of squares anyhow for factoring. Well, it doesn't look like there's anything else to factor. Then we do a partial check, and this is a good strategy for checking our factorization. So if you think about this, is again, we have this original polynomial, this 4-term polynomial, and we say, well, another way to write this really is to say that this is the quantity x plus 5 times the quantity 2x squared plus 1. In other words, they should have the same solutions or same effect on any numbers that I put in for the variable. And that's where they go with this one. Let's say, let's do a check with some number, right? In other words, for this to be true, it means that this needs to work for all values that I could substitute in for x. So I can't, this isn't really proving that I have the right answer. It's just a partial check they talk about. So they put 2 in for x and see what happens in the original. So here's where they put 2 in for x. Remember to use order of operations, that you have to cube this 2 before you multiply times 2. The big difference between 2 times 2 cubed compared to saying I went 4 to the 3rd power. You're going to get a lot different number and you'll get that incorrect. So make sure you follow order of operations. Here I have to square that 2 before you do exponents before you multiply. And I do that and I get the result here is of the valuation of this polynomial right here when x is equal to 2 is 63. Well, I do the same thing with my factoring, right? I put 2 in for x and what do I get out? And in this case I get 63. That's a pretty good indicator that your factoring was done correctly. Now you should watch out for values when we get into more complex stuff, when we have division by variables. There's certain things you can't use like 0. And 0 is not a very good value to test with. You know, I could get into some troubles. In this case it wouldn't be a problem, but there are some instances, especially if I have a variable in every term of my polynomial, putting 0 in there. It's nice because I end up with just 0 plus 0 plus 0 plus 0 or whatever. And you can do the math fast, but it may not be a good check method. But this is, you know, they don't go through this in strategies very much. They usually just show this in examples. This is a very good thing to do. You know, some of this factoring can take a long time, especially when we get into it. We're going to talk about prime, things like that. You might spend a lot of time trying to figure out what's next. And boy, when I get done with all that work, I would like to know if I did it right, or make sure that I just didn't do some simple error after spending, you know, maybe 10 minutes on a problem. So check your answer, okay? You can always check. This is one method. The other method is to multiply back this factoring, see if you get the same original polynomial. Example 3, we have a negative 10 n to the 5th minus 80 n squared. First thing again, look for common factors. Now they do something here which is also a nice thing to remember. You know, we're used to that first term of most of our factoring strategies or patterns that we see is this is positive. Well, I can always factor out a negative 1 and change the signs of any terms. And that's what they do. Instead of saying, well, let's take the common factors here of 10 and then we have n to the 2 powers factor. I could say a negative 1 is common. But even if this was a positive 80, I'd probably want to change the sign in my first term. We get used to our patterns showing that the first term is positive. So I can factor out a negative 2. So they say the common factor here is a negative 10n squared, and so you end up with this resulting factoring right here. Then the next thing is, well, can I factor anything else? Well, I have n cubed plus 8. Well, 8 is 2 to the third power. Again, prime factoring will help a lot here. You might miss that, hey, this number really is a perfect cube, but if I prime factor 8, I get 2 times 2 times 2, or 2 to the third power. So really I have n cubed plus 2 cubed. Hey, that's a sum of cubes. I can use a pattern and factor that. Then I check this. There's more than likely, I think, I don't know if I can prove this or gone through this, that this trinomial is not factorable, but you can check some, see if you want to take that time. But usually when we use a pattern like sum of cubes, the resulting factoring is prime. In other words, there's no other factors that we could work with. So it says no factor can be factored further. I would wish that they would use, proper terminology really is all factors are prime. Okay, so we're done. Now in this case they check, the D part is to check. Well, they take our factoring and multiply it back. Then what I would do then is check my pattern here and say, hey, does this really give me the sum of cubes here? And make sure of that. But I also could distribute, would be one way to check that too. I take n times n squared, n times a negative 2n, n times 4, and then distribute the 2 here. 2 times n squared, 2 times negative 2n, 2 times 4. Add all those terms up, and you should end up with n cubed plus 8. And then if I multiply my common back into this sum of cubes, then I would end up hopefully with exactly the same polynomial that I started with for a check. Ugh. Example 4. Factor 6x squared y to the 4th minus 21x cubed y to the 5th plus 3x squared plus y to the 6th. Now, definitely getting more complex, right? And this is why we should always look for common factors first. When I look at that, I'm going like, whoa. If I had to just say, hey, I have a trinomial now, what do I do? This would be very difficult. So I look for that common factor. In this case, the common factor is 3x squared y to the 4th. And, I would do this by listing the prime factors, which I would, it's pretty easy to see what the primes are on x squared and y to the 4th. That's x times x and y times y times y times y, right? But sometimes it's very easy to miss the coefficients for common factors. So I would say 6 is 2 times 3, 21 is 3 times 7, and 3 times 1, right? That's prime is 3, right? Hey, then I can see, hey, there's a 3 factor, and a 3 factor, so I make sure that I do that. Again, I recommend that's a very good strategy to make sure I catch my largest common factor. It'd be very easy to go in here and miss the 3, take out the x squared y to the 4th, and it's still possible to get the right factoring, but it's just created a lot more complex trinomial you're going to have to work with. So get that largest common factor. Using prime factoring again is a very good tool. Well, we factor that out and we get this multiplication here of 3x squared y to the 4th times the quantity 2 minus 7xy plus y squared. So what is this? Well, it's not a binomial, so I don't have to look for difference of squares or sums of cubes or differences of cubes. It's a trinomial. There's 3 terms. And they point out a very good point here. I could go, well, I need factors of 2 and then factors of y squared, and you could start doing anti-FOIL. But if you think about this middle term, is there any way I'm going to get an inner and outer multiplication from FOIL that's going to give me a product, basically a answer to that multiplication that's going to have this new variable x in it? You know, it's always going to be products based on multiplying these two things together and adding them. So what they're pointing out is there's no possible way to get an xy or another variable in the middle term of a trinomial. So in other words, if I'm going to factor this into two binomials, or actually use anti-FOIL or grouping or methods like that, it's definitely not a perfect trinomial square. I could look at that right away, and in fact that's usually where I go right away to say, hey, trinomial, look for that, right? Well, 2 is not a perfect square, so I'm done. Okay. And but they're pointing out, hey, look at this middle term. It is not possible. I'm not going to go down that grouping or anti-FOIL method. If I just kind of think about what has to happen for these middle terms to occur this way, there'd have to be an x part in this first term, like 2x or something like that. So what they're saying is, oh, well, based on that, this can't be factored, so I'm done. And so nothing can be factored further, so I'm factored completely. Then they check here by multiplying back, which is just the common term times this. But again, I do fully understand when you run into something prime that's a little more complex. That's what this is, prime. It's not factorable. The only factors of this trinomial are 1 in itself. That means it's prime. It can take some time. If you miss things like that, you're going to go like, you're going to have to do a lot of anti-FOIL experimenting, possibly on some of these, and then say, it just doesn't factor, so I'm done. Okay. So this is a good example. So notice how the examples point out, hey, you know, watch out for this. This is, you know, these things. Let's give you a few hints, might save you some time and effort on these problems. This is a good example. 5. Factor 98x cubed plus 280x squared plus 200x. Well, when I look at this right away, I know that there's a variable that's common here, which is x. I just don't want to miss the largest common coefficient factor, right? So I probably prime factor these and so on and make sure. In this case, it's 2. Well, I know 2 is going to be a factor because they're all even. You know, I start using a lot of this tie-ins to, you know, divisibility rules, that kind of stuff. But I probably still am going to prime factor that. Like 200 is not hard to prime factor. It's 2 times 100, which is then 2 times 2 times 50, 2 times 2 times 5 times 10, you know, and so on. I mean, it isn't like it's going to be tough. And these are not too bad either. So what we find is that the common factor is 2x. You take that common factor out. Now I have 2x times this trinomial as a result here. So I don't look for difference of squares. I don't have to look for sum of cubes. I don't have to look for difference of cubes. But I do want to look for perfect square trinomial first. And in this case it is. So I look at the first term as something squared is 7x, the quantity squared, right? They end up with this right here, right? And 100 is 10 squared. So the middle term is positive, so I'm going to use the positive 10. And I end up with checking the middle term is 7x times 10 is 70x. If I double that, yeah, I get 140. So it fits the conditions for perfect trinomial, or perfect square trinomial, excuse me. So we end up with 2x times the quantity 7x plus 10, the quantity squared. Then I look, well, can I factor 7x plus 10 any further? And the answer is no. This one, again, they do that partial check. They use 1, they put it in here. Here would be an example where 0 would work, but I would suspect that, you know, because anytime you multiply something by 0, you're going to get 0. You could get a false idea of a true solution. So Don't use 0 in these things, especially when you have a variable as a common factor. So they use 1, they go through that to get 578 for the first original. Then you put 1 into the factoring and you get 578. So that's a pretty good partial check to see, hey, my factoring looks like it's working, and that's probably enough work to check. Example 6 is we have this trinomial, which is negative 10 m squared minus mn plus 3n squared. Well, look for common factors. Well, there's 2 and 5 are prime here. There's a negative 1 is the only thing for, and a 3. There's no common coefficient factors, and there's m here. I got m and n, but I don't have an m here. So there's no common factors for any of these terms, and do that. Now, here we're used to working with patterns with a positive first term when we get to trinomials. So we're going to look for perfect square trinomial. But the first thing they do is say, you know, it'd be good, or it'd be easier, really, if we had a positive first term. I can change the sign of any term in this by factoring out negative 1. So if I factor out negative 1, this negative 10m squared changes to a positive 10m. This negative mn changes to a positive mn. And this positive 3n squared goes to a negative 3n squared. There's some other ways we could do that. Because these are terms, if we treat them as addition, I could change the order of this thing. And I could actually put the 3n squared up front. And that would have taken care of this too. But let's look at how they do this, and why I appreciate that they go through this, because there really are, you're going to run into some times where it's going to simplify things tremendously if you factor out that negative 1 or change the signs of the terms. That's what you're doing. Well, there are 3 terms in the parentheses, so now we have a trinomial, and they check to see if it's something squared. Well, I look at this, either one of these first or last terms here, this is not a perfect square. 10 is not a perfect square, and 3 is not a perfect square. In fact, I have a negative first or last term either way, right? Means that it can't be a perfect square, because I can't square something and get a negative number anyhow. So what they're going to go to is FOIL, and they go through the FOIL method here nicely, and we have 2 possible combinations to start with the first term, because we could take 2m times 5m and get 10m squared, or we could take m times 10m and get 10m squared. You know, so this is just really a review here of using FOIL to factor this out. And then we have, that's why they list the factors of negative 3n squared. They actually do it twice here. So it's like we're going to plug these in here and see if they work for these. And the reason that they're still here in a different order too is that order does matter because the coefficients are different. So we have really 4 possibilities for each one of these to test. Okay. So they check the possible combinations. They figure out that, hey, this 2m minus n and times quantity 5m plus 3n works. So I end up with that. Multiply that, and then do not forget your first thing you did, right? Which is, could be easily turn out to be an error, is you forget that you factor out negative 1 to start with. Make sure you put that back into your factoring. Now if you check, you should catch that. And if I catch that kind of error with a check, I'm going, oh, that's easy. I just put the negative 1 in front, and that's my factoring. Okay. They also show that there are some different possibilities of how this might lie here, or how we can write the negative 1 times it, or the opposite of it. I would even take the answer, if you multiplied the negative 1 times this first binomial, you'd get negative 2m plus n times 5m plus 3n. That, I think, is sure a valid factoring. And I think that even my math labs will take it either way. So let's look at example 7. We're going to factor this thing out here first, look at it. Are there any common factors? Well, uh, 12 is 2 times 2 times 3 is a prime factoring. None of those are factors of 7 or 1. Okay, so there's no common factor. Since only one term is a square, we don't have a perfect square trinomial. So first thing they check for that perfect trinomial, because it's a trinomial, is, hey, 12 is not a perfect square. So it's not going to be that. So then they go into anti-FOIL, and they write out the factors of how do I get x squared, y squared. It would be xy times xy. And then we start looking at factors of 12, which could be 1 and 12, 2 and 6, 3 and 4. And what you might want to notice is 2 is that the pairs 3 and 4 have a summand of 7x. And I can say that's one that's going to work, right? Sometimes FOIL is definitely, on a simple trinomial, is a good way to go. They're just showing a little more, in this example, just a little more complex first term. But it's really the same strategy, right? So then we check, make sure that each one of these factors cannot be factored any further, or another word for that is xy plus 3 prime. And it is, and xy plus 4 is prime. So I'm done factoring. And then they check by multiplying back, make sure you get back to your original. Okay, example 8. Well, we go through our A, B, C, D again, right? And this case, we look for common factors. Well, we got A as a factor here. We have 4, or 2 times 2 times 2 times 2. Actually, 16 is 2 to the 4th power. B to the 4th power, which is going to be important to look at too. That's where prime factoring again can be helpful. Okay. So, no common factors. Now we have two terms, so what we're going to look for first is difference of squares. Well, that is a strategy that hopefully I can use, because it's better than sums of cubes and those kinds of things too, which we're going to run into an example where we could go either way, and you're going to end up stuck if you go the wrong way first. And so to get a difference of squares, I need to think about, how can I write a to the 4th as something squared? Well, it's really a to the 2nd squared. Okay, and that's what they're showing here. If I take a to the 2 power to the 2 power, power of powers is 2 times 2 or 4. Well, 16, I went to 16 is really 2 to the 4th power, but they just recognize that 16 is really 4 times 4, or it's the square root of 16 is 4. The square root, another way to say square root of b to the 4th, is b to the 2nd. Or in other words, I can rewrite 16b to the 4th as the quantity 4b squared all to the 2 power. And if you perform that, make sure, this is an order of operations issue. I can say that's really 4 squared, or 16, and then you multiply exponents and get b to the 4th. Well, I have something squared and something squared, and I have a difference. That's difference of squares. So I can look at this and I say, well, I could factor this to be a squared plus 4b squared times the quantity a squared minus 4b squared. And that's the factoring of difference of squares. Now C, they're really doing the C part. Are you done factoring? And they're, instead of saying, hey, we're done factoring, they say, no, I actually have another difference of squares right here. This is sum of squares. We don't have any rules for that or any shortcuts, but here we have something squared minus something squared. So I can factor this, and that's where we really got to do, is make sure you factor completely. I'll catch a lot of answers, especially on tests, where you'll take this, hey, I recognize that, and tell me this is the answer. Well, I need to factor this completely. So here is another one. This is difference of squares. So I'm going to factor a squared minus 4b squared to be a plus 2b, and this other binomial a minus 2b. And they say that's a factoring of this, right? Now I check all my factors. Can I factor any more? And now C says, the C portion of my strategy, no, I'm done. There's nothing I can factor further. And then I multiply to check in this case. So I end up with this original, or hopefully I get back to the original, right, polynomial. And that's the last one of those. So good luck on this assignment. If you picked up that other video, this is a redo, and I'll try to get rid of that other one, and hopefully it'll catch you if you watch the other one. I think this one's, I'm definitely talking faster. I'm less tired when I was working on this one. So good luck on your assignments. We're coming up close to the end of the chapter. We're going to start doing some quizzes and the proctoring for the chapter test. I'll get some messages out to tell you when the window of time to get your proctoring set up, and I'll talk to you later.